So nice to be here. Nice to see everybody. Nice to be in person. I am going to keep it to less than an hour. I am okay with people interrupting with questions that relate to like the immediate stuff I'm talking about. However, if you would like to have a philosophical debate, which I am totally happy to have, we will do that at the end. So, if you start to ask me things like, why does embodiment matter? Or why a robot? Hold on to those. All right, but otherwise, feel free to interrupt. I'm happy to clarify. All right, so I'm going to talk to you about this field of socially assistive robotics, but, I'll tell you what it is. So I'm a roboticist. I've been a roboticist for a long time, too long. Well, there's no such thing, but anyway, longer than I'd like to say. And we're finally getting to a point where companies are now building robots that will go into our homes. I mean, there are robots already in factories. There are some robots in our homes, like robot vacuum cleaners. If you have a Roomba, Roomba is the most, it is the robot that is in the most homes in the world. And it has now just been acquired by Amazon, whatever that means. So, maybe there'll be more of it, maybe there'll be less of it, who knows. Anyway, the point is we do have some robots already in our homes, but we're just starting to get to a point where we're starting to develop machines that are interactive enough, intelligent enough in real time, and have basically the physical bodies that might, not quite yet, but soon, might be safe enough to have in environments like homes. And so let's look a little bit ahead and say, well, so now that we're sort of almost there, and it's going to happen in my lifetime, yay. What happens? Well, here's what happens. There have been a lot of studies already in the field of human-robot interaction, which is now about 2 to almost 3 decades old, that have looked at how people interact with robots. Now, these are people like us who are not used to robots. Okay, I'm used to them, but most other people are not. So we can't predict what it'll be like when people grow up with robots, but we can talk about what it looks like now. And what we do know is that when you put people together with even the simplest of machines that are sort of lifelike, so it could be like a little thing with wheels. It could be a trash can-like thing with wheels, or it can be a full-body humanoid that has no idea what to do with itself. What happens is we as humans, because of the way we're wired, we're social creatures by nature, we are going to assume that the machine has some kind of intentionality, that it has agency, often that it has thoughts and goals and intentions and even feelings, okay? And this is just what we're loaded with, so you can't help yourself, right? And you feel relatedness to the machine, you feel kind of compassionate for it, you feel empathy, but also, depending on the way that the machine was designed and or depending on how it behaves, you also can feel creepiness and what's called cognitive dissonance when there is a difference between how the machine looks and how it behaves, or what it promises and what it delivers. And in fact, we as humans are complicated, messy creatures in many ways, and people have certainly done a fair amount of bullying and abuse of robots that exist today. So basically, what this tells us is that as we build artificial machines or artificial, well, I won't say AI because that's such a broad and loaded term, but let's just say as we build intelligent robots, they're kind of a reflection of ourselves. And they bring out interesting things in us. They could bring out the best in us, and they can bring out the worst in us. And they've already done this in studies. This has already happened. And not only in studies, it has happened in the real world. There are stores in Japan where people have, punched and thrown down robots, and there were videos on YouTube briefly, and they were taken down, and so on. There are all kinds of interests of why people might not want you to see this, but there's certainly a spectrum of behaviors that machines elicit in people, because we as humans are loaded with all kinds of biases and complexities. So then how do we create machines that we're going to accept and that are going to bring out the best in us and not the worst in us? And I can tell you right now, there's no good answer. There's no good answer because we are complicated creatures and we disagree on the most basic things like, pandemics and masking. And therefore, we're going to disagree on pervasive things in our future, such as AI and robotics. But I can point out one way, which will be the theme of this talk, one way in which we can get humanity to hopefully agree around some uses of robotics, and that is around the balance between automation and augmentation. So the vast majority, 90% of all robotics to date, which means all of the past decades of robotics, and we can debate if it's been 50 years, 60 years, depends on where you pick the beginning, but however long it's been, the vast majority of effort has been on automation. So the idea is we take some process and we try to remove the human out of it and put a machine into it because that's safer and cheaper, more scalable. Machines don't get tired, they don't get sick, you don't have to pay them, etc. Right? Now, on the other side of that is the notion of augmentation or enhancement, where the machine is improving the human's ability to do something rather than doing it for them or instead of them. This is a continuum, right? So no one is saying it should be one or the other. But the reality is that it's mostly been automation and not augmentation. And so I want to have us think about, what does the augmentation side look like? Because the original people who came up with the ideas of robotics and AI were talking a lot about augmentation, and some of that got lost in history. So I want to tell you about how robots can be useful and lucrative. So there's a large business proposition, or several of them, by not just doing our work, but helping us do the work ourselves. So empowering us. And I particularly want to tell you about this field of socially assistive robotics. This field is now 2 decades old. I feel old. It was named in my lab at USC, so nearby, by a student. And it's a field. What makes a field? Well, if you look at how many papers have been published in it, it's tens of thousands. There are companies that develop these kinds of robots. If you Google it, you'll see it. Of course, there's funding that you can get from the National Science Foundation, from NIH, from DARPA, to do research on it. It's a field. It's a thing. Now, you might have heard of social robots. Social robots are robots that interact with people socially, but they don't necessarily have a purpose. And they certainly are not necessarily meant to help someone. Socially assistive robots are very specifically 2 things. Well, 3. They're robots. They have to be physical machines. A robot is always a physical machine. We talk about chatbots. That's just the word. These are not robots. A robot is a machine in this world with us. That is a robot. And that's really important because it's a lot harder to create a machine in this world than it is on the screen. So, socially assistive robotics, 3 things. It's a robot, so it's a physical machine. It's assistive, which means it does something that measurably helps a human, measurably. So it's not enough that it makes you smile and makes you happy like social robots do. It actually does something measurable. And does it socially. That's the first part of it. So it doesn't do it physically, it does it socially. Because there is a field of physically assistive robots. For example, machines that help stroke patients move their arm. That's physical assistance. That's a wonderful thing, but that is not what we're talking about today. So why is this important? Why would we even want to do this? Here's why in a nutshell. So if we're interested in helping people do something that they need to do themselves, it turns out we can monitor human behavior, right? We know this. This is a quantified self, right? I have an activity monitor. Most people have something. It's great. It gives you numbers. Does it change your behavior? No. Statistically speaking, and now we know because we've had Fitbit-like devices for well over a decade, statistically speaking, most humans do not change their behavior significantly or in a sustained way based on just being given data about their behavior. You know your stats, you know your cholesterol, you know your exercise, you know your weight. How many of you have now said, that's great. This is it. I need to lose 3 pounds. I'll be done in 3 months. No, not really. So it's very hard to do behavior change. Just having data is not enough. So the quantified self is not enough. Okay, now, what does work is coaching and training. So when you have some social pressure, whether by a person who is there, who you're paying, or who is guilting and shaming you, or who is a friend that you promised you would do this with, these kinds of things really tend to change behavior. So it's all about motivation. If we're motivated to do something inherently, intrinsically, then we're going to do it. Or if we're motivated externally by social influences. What doesn't work is nagging. Those of us who are parents know this firsthand. You can keep telling someone to do something, and if they have to listen to you, like if they're a small child and they're dependent on you, they'll do it, but as soon as you're gone, they'll stop. So extrinsic nagging doesn't work, but extrinsic motivation does work. And so what it all boils down to is you need some kind of companionship or social support. And that turns out to be a sweet spot for a lot of different technologies, but very few actually change behavior. So when we look at large areas of health, mental health, things like weight control, cholesterol, heart disease, everything, we need to help ourselves manage how we behave. We need behavior change. And we're having a hard time making that happen, especially because there aren't enough people to help people. So that's the niche that I want to tell you about, where There is a clear business proposition. And I want to tell you what's happened in the last 18-ish years. So in the early 2000s, we started out with these short-term deployments, like go for an hour to a cardiac surgery rehab, or go for a couple of hours to a pain management clinic. And then it took about 10 years, and then we started to do multiple sessions. And now we have machines that we can deploy, and we as a field have machines that we can deploy in the home for a month at a time. Or in one case, we did a study with an elder care facility, and we left the robot there for 6 months. There are very few companies as yet, well, barely any, and they're all startups. None of the big companies yet have robots that are putting in people's homes. Maybe soon, maybe not soon enough. There's a lot of liability, so that's, a lot of logistics are keeping people out of it. But it's almost there. And so let's talk about what it takes, why is it important, why is this not happening, things like that. Yes. Robotic pets are not necessarily, so do robotic pets fit these categories? So they're not socially assistive in the sense that they're not explicitly measurably helping something, because they usually, so most of the robot dogs don't talk, nor should they. That's very creepy. Dogs don't talk. If it talks, it's not a dog, it's something else. So you really, if you want it to be really socially assistive, you want it to have measurable outcomes. It could be a social robot though. So the Sony Aibo is a social robot, right? It's a really cute, very sophisticated, quite overpriced piece of electronics. But does it measurably do something? Predictably, no. Because it isn't programmed that way. It could be, but it isn't. Okay, yes. Yes. That's kind of a big theme. So, okay, so the first thing, although not, this is kind of almost an afterthought, but one question you can ask is, what do these robots have to look like? Because there are two questions people always ask and should ask. One, why should it be a robot? Why should it be a robot? And we'll get to that. That's like 3 slides away. You should always ask that. If you could do it with not a robot, if you could just do it on the screen, then you should, because it's cheaper and safer, but it's not as effective. So if it is going to be a physical robot, then what should it look like? Well, there is no single answer, and it's a complicated problem because you can't kind of do trial and error. It's very expensive to build a robot. So you can't kind of say, well, I'll try this one. Oh, I didn't like that. Let me try this one. I mean, it's very hard for a company to basically hone in on a specific design that's affordable, has the right affordances, and then just build it. So we did some studies to figure out what kinds of embodiments are received in various ways by people. And people are very biased. And so one of the things we did is we looked at the data set of 165 robot embodiments. That's the IEEE data set for all of us who are IEEE people, and ACM as well. And we looked at on a bunch of measures. And it is actually quite important. There's certain embodiments of robots, like there's the Sony Aibo, that you're only going to find believable and acceptable for certain functions and not others. And that's very important because companies right now don't understand this at all. So they build a robot and they make it look a particular way because in the best case, they get a design firm to design it, but the design firm has no knowledge about how humans and robots interact because it's so new. And so people are developing things, throwing them over the fence and seeing what happens. That's expensive trial and error. But it turns out there's some science that we can actually look at in terms of when you look at a particular embodiment of a robot, what do you think it looks like? What do you think is it trustworthy? Is it believable? Does it look competent? What would you use it for? Those are the kinds of things we need to understand so that when people start designing machines, they're actually acceptable and believable. And so we did a bunch of science on this. I won't bug you with the details. These are all publishable things, or published things, but some of the things that are important are things like a robot dog versus a humanoid robot. They have great differences in possible acceptance, trust, and function. So that's just one obvious thing. And then you might be surprised, but there's a lot of gender within robots. So if I show you any robot at all that is humanoid-like, and I ask you, what gender is it? Chances are you'll say male. First of all, you'll be ready to say that it has gender, which is wild. These are machines. Why would they have gender? But you're wired to perceive gender. And so you're going to perceive it, and you're going to tell me, and likely it'll be male. Most people think most robots are male. Why is that? We don't know. So that's interesting. And then it turns out when you actually take kind of a generic looking robot that isn't gendered, I hope, I don't think that middle thing has a gender, and then we slightly skew it to be slightly more traditionally male, slightly more traditionally female, you get all kinds of biases to pop up. So if I tell you it's a nurse, then you think it's female. If I tell you it's a doctor, you think it's male. Wow, I wonder where that comes from. So these biases are important, however, because again, they have to do with what we're willing to accept in terms of technology. So there's an entire area of human-robot interaction that's just trying to study these kinds of things. It's not really my field, that studying robot impressions, but I had a student who was interested, so we did a couple of studies. But now to get to the heart of the matter, why should we use robots? For all the things that I'm going to tell you for the rest of the talk, and there'll be a lot of machine learning models and many, many fun things. But why are we using physical robots? Why don't I just do this with simulations? It would be so much easier and so much cheaper and so much faster. Well, because a huge body of work over the last 20 years has shown that we look at human-machine interactions. When you look at a human interacting with a screen versus a human interacting with a physical robot, people who are interacting with physical robots experience more enjoyment. They learn more from the interaction if there's a learning task involved. They retain the information better. They trust the machine more, and generally they prefer it. And if behavior change is involved, like I talked earlier, then it's much more likely to be sustained. So there's a reason why. We know there are a bazillion apps out there for behavior change, and bazillion -3 don't work. Because if apps fixed your life, wow, wouldn't that be great? We'd all be done. We'd all be fixed. It doesn't work. It's harder than that. But if there's a social agent in the real world that's kind of like you, and that is that embodied robot, then you're much more likely to actually change your behavior. So we did a review paper over a large body of other work over the previous 20 years to show that. And it's not surprising because neuroscience already shows us that. Neuroscience shows us that your brain behaves differently when you're interacting with a physical machine than when you're interacting with the screen. And these are actual images. I didn't do this. This was Ralph Adolph's at Caltech. And then if there's physical contact, there's even more engagement. And we're not, for the neuroscience people among you, if any, we're not talking about like the tactile cortex here. We're talking about the part of your brain that engages just because there's more interaction going on. So a screen cannot do that. But I know what you're thinking. You're thinking, oh, but what about the metaverse? What about virtual reality? Oh, I know what you're going to ask. I have graduate students. So why not? Why not the metaverse? Well, it turns out mixed reality is a wonderful thing. And in fact, it's going to extend robotics. It's going to extend human-machine interaction. I just spent 2 hours today talking with a bunch of colleagues across the US with the National Science Foundation about mixed reality for people with a diversity of needs and abilities. So it's a very relevant technology. But you cannot put a human in a cave and do virtual reality and then pull them out of the cave and expect them to generalize to the real world. So that's really important. For example, let's take kids with autism. Let's take, actually, we'll get to kids with autism in a little bit. Let's take people who have various kinds of PTSD. You could put them in virtual reality and it could be an effective therapy, but generalizing from virtual reality to the physical world can be very hard and sometimes doesn't work. So you can do a lot in virtual reality. You can trick your brain to believe that it is in that other world, but it's in that other world. It's not in this world. And so if you really want things to change in this world, you'll have to make them change in this world. So augmented reality is kind of an interleaf in between. And that's really exciting because we can, for example, we've done a lot of work with light mixed reality, where you literally use either a phone or a tablet, not goggles. Because once you have goggles on, then you're not in this world. You're in the goggles. Now, when Google Glass of some kind comes back, I don't mean that it'll be Google, although maybe, right? When you have something that is very light, so you're interacting with the world normally, but you also have this extra overlay, that's very empowering. Right now, we do that through screens. So there's a lot that you can do. Like we have done experiments with these robots that are not physical, and then also physical robots, and showing kids, I'll tell you about that in a little bit, showing basically kids how to code in real time by moving around. And it's very effective. They learn to code better, and they're much less afraid to make mistakes, which means they learn faster. So we'll get to the metaverse, but my students hate that word, and I don't blame them. We're not in the movies, people. We're in the real world. But it is a new frontier. I do agree that it's a new frontier. So for example, the kinds of things we've done, we have had elderly people this is not an elderly person. This is my student. We cannot show pictures of our actual participants because of human subjects laws. But we have had robots, for example, be able to communicate through mixed reality to the user what they're sensing. So when you look at a robot, you have no idea what it knows. You don't know what it knows. You don't know what it can sense. But if you use something like augmented reality, the robot can project for you its intention, where its sensors are, what path it's going to take, what it sees, what it's thinking. So you kind of have a shared world, which can build trust. So that's just one example. We've done a bunch of other things with mixed reality, and other people are doing interesting things as well. Meta? What's meta? Mm-hmm. Yeah, that's what this is. This is physical, not virtual reality. You cannot have a robot in virtual reality that's real. Because once you're in virtual reality, you're in virtual reality. You're not in physical reality. To be in both, you need to be in so-called mixed reality, which is augmented reality, not virtual. Just think of virtual as virtual and real as real. The thing in between is augmented. And that is exactly what we did. Yes?
How is connectivity coming here? Is it like Wi-Fi direct, or is it like Wi-Fi common? Or?
So this is Wi-Fi. Yeah, this is all Wi-Fi, because you can tell that there's, he's just wearing a headset, or we're just wearing we're just using a tablet. So, yeah, I mean, you could talk about bandwidth and things like that, but that's really hasn't been an issue. We're not trying to send anything that's massive, right? You're not trying to simulate. The whole point of augmented reality is that you're not trying to simulate some super complex world. That's virtual reality. That's like what Meta is trying to do. They're trying to create all these worlds, and they're hoping people will show up, right? You don't need to do that when you're in the real world, because the world is right there for you. You're just augmenting it. You're adding a little bit. And really, the less you add, the better. Just the right thing.
Is there any connectivity between a robot and your mixed reality headset?
Oh, you mean if they're sharing state? Yes, of course. So that's the whole point, for example. And in this case, and I'm going to get to that in a little bit, but later in the talk, but just so that it's clear. So for example, the robot this is a physical robot, which also has virtual arms. And it's reaching to virtual objects, because in the robot's mind, it can see these objects. And it's seeing the same thing that the human is seeing, because they're sharing state. Okay? And that's the beautiful world about augmented reality. That's a beautiful thing, because in augmented reality, the machine and the human have this shared world that doesn't really exist for anyone else. It exists for the two of them, if that's what you want. Or it can exist for a group of people, whatever you'd like. All right, but I really want to pull out of the metaverse and get into this universe here. So I want to talk about something entirely different related to embodiment, right? So we've talked about it's important to be in this physical world. Sometimes you can augment the world by having augmented reality. But why is it so important that it be a physical robot? Well, there's some domains in which nothing but a physical robot will do. And here's one that I bet will surprise you. We were fortunate to be the first to do work with human baby infant interaction with these infants in as you will see, we're looking at infants who have trouble moving their limbs. So they have early delays, and if they're not helped, they may have permanent disability. And so how do you get a baby to move in a particular way? Here's a spoiler, you can't. You cannot tell babies what to do. Nope, you also can't tell kids later what to do, but at least they understand you. Babies do not understand you. So what you could do is you could trigger their imitation circuit, but not as an adult, not as a grown-up, not as a child. You have to be matched in size to the baby. What's matched in size to a baby? It's another baby. If you can tell me how to train a baby coach to tell another baby what to do, great. But until we can do that, you use a robot. And so the idea here is some very, very brave students of mine actually developed a robot that they could, well, a system, this is a commercial platform, Aldebaran, that basically can behave in a particular way so as to make the baby imitate and behave in a particular way so that the baby would make movements to practice, okay? The practice is fundamental. Otherwise, if the baby doesn't do movement babbling, it doesn't have normal development for these babies who are delayed. But more importantly, the mother can't do it. The father can't do it. The occupational therapist can't do it. You can't just move the baby's arm because you can move it, but then they're not learning. They have to move on their own volition. How do you make them do that? So the robot is actually a unique way of doing it. Oh, by the way, I forget to mention, the screen won't do it. Babies can watch the screen, and their visual neurons are firing. They're watching the screen, but it's not making them imitate. And they're also not retaining what they're seeing. They're unable to learn from the screen until much later in life. Not much later, as in, a few years. Okay, so yeah, you can't do everything with screens, and people giving 6-month-olds screens to swipe, not a developmentally appropriate thing to do. So I will tell you in a little bit what's actually happening. There's a bunch of math going on behind that, which I'll show you. But the beautiful thing is, this is the only way to actually get the baby to do this, which is kind of exciting. We never could do this until we had robots. Okay, so the goal is to make people better with socially assistive robotics. And that has two meanings: make people feel better and also make people behave better. So I will tell you about that. And now we're going to get into computational modeling and things like that. I mean, this is the ACM or IEEE, either way. So the goal, get people to do things that they need to be doing to help themselves. The challenge is, how do you generate and sustain motivation and grit? The approach is, we're going to find behavioral phenomena like engagement, like motivation, you'll see. We're going to model them computationally, and then we're going to use machine learning to personalize to each user. Okay, so first of all, social dynamics. So we talked about embodiment. Now we're going to talk about social dynamics. Turns out everything matters. So when you're interacting with another human, just like when you're interacting with a machine, everything matters. Turn taking, who looks at whom for how long, who speaks when, what's their body pose, how close are they to you, are they gesticulating? All of this matters. So when you're creating socially interactive machines, if any of that isn't quite right, people think it's creepy. You get that uncanny valley. And it's quite complex, right? And so now, how do we do all of these complex things? What are the roles of the robot? Is it an equal? Is it a subordinate? Is it a superior? It certainly can't be mixing these things, because that's definitely creepy. Is it a coach? Is it a tutor? Does it understand your intent? Does it understand what you're doing? These are the things that people are working on, because if you're going to put robots in, let's say, your home, they need to know what you're doing, who you are. They need to not be dangerous. They need to anticipate what you want. They need to know what you don't want. All these things. Otherwise, you're going to say it's really frustrating and you don't want it. All right, so let's get back to the baby so you can know what it takes. It may look like the robot is just moving and then the baby just does things. It's a little bit more than that. So in particular, what we were interested in is, how can we predict where the baby is going to look? Because where the baby looks, that's what the baby is going to observe, and then that's what the baby is most likely to imitate. So it's a Bayesian probabilistic arc, where if I predict where they're going to look, I can predict how they're going to move. So there is actually a model of surprise. You will look where you find things surprising. Can I predict what is most surprising about this image? Right? So there's a model of that was built by Laurent Ity and Pierre Baldi. Ity is actually my department. This is what happens in academia. He did this 20 years ago and I had no idea. Okay, maybe not 20 quite, but okay. In my department, had no idea. But then we read the paper, we're like, oh, look at that. So we can predict where adults are gonna look. Does that mean that we can predict where babies are gonna look? Well, generally, there's a lot of difference between babies and adults. And almost nothing that is trained on adult data works with babies. But this does, because early vision, surprise, visual saliency is low vision. It's early in the visual process, so babies even have it. And so there's a model that predicts in a given image where the baby is going to look. So I can make the robot move in a way that's going to draw the baby's attention, and then make the baby move, like if I want him to move the right arm, the left arm, and so on. So that's an example of how you're using a computational model to predict human behavior, in this case, an infant's behavior, in order to then drive that infant's behavior. If you really think about it, it's a pretty beautiful loop. And there are not a lot of examples in general of human behavior where you can model and predict something and then do it to reliably make the human do something. That's kind of the challenge. But we'll give you lots of examples of that. Another thing that we have modeled is bullying. So I want you to hear this. Can you hear it? So basically, what's happening is the human is doing threatening gestures and actions, And the robot is saying things like, don't do that, that is really, like, don't do that, that's demeaning, or don't do that, that's threatening, it's socially inappropriate, and so on. And so we were interested in understanding how we can detect bullying. Bullying is non-trivial because it's easy to detect things that you can get out of Skype data or YouTube data, things that are easy, like pointing. Oh yeah, I mean, they're models for pointing, that's easy. Bullying is a very tricky thing. It's usually covert. People don't generally want you to know that they're bullying, and it manifests in many different ways. And so we were interested in developing a machine learning model for detecting bullying. Why? Because kids bully. We wanted robots to automatically detect bullying and then teach kids not to do it. Because sometimes they don't know they shouldn't do it. And so basically, how would you do that? Well, how would you build a model of a behavior that no one wants to do? And here's a tip. You might think, well, we'll just have people act it out. So we generally think that if we want to have more data, maybe we can get people to act it out. Doesn't work, because acted behavior isn't real behavior. So there's been some beautiful work to show that you can, for example, take behavior from, like, let's say a show like Friends. I think we all know what Friends was. That was popular for about 15 years. And the acting there is really believable, right? You watch the show, you believe they're feeling those emotions. But real people do not act like that. That's overacting, right? Generally, acting is overacting. So that if we find something believable in a movie, it's overacted compared to normal behavior. And so if you train models on acted data, they are not sensitive enough for real behavior, and they can't deal with noise, and they can't deal with diversity of behaviors. So we wanted real data. So what we did in particular was we created the sensitive robot, and then we had a tour with 2,000 kids that came through for our robotics open house, and they interacted with the robot, and they all immediately bullied it because it was sensitive. So it was a brilliant move by my graduate student, who basically, as soon as the robot said, don't show me your fist, it looks like you're gonna punch me. What do you think kids did? They immediately went like that. So we got a lot of real data. But the thing about collecting data about sensitive, non-obvious behaviors is the major challenge of AI today. So there are these massive models being developed, but unlike language models where you have all of the internet of data, in every other domain, there's a paucity of data. Okay, here's one that everybody loves to hear about: detecting lying, detecting deception. So this is very interesting, right? So wouldn't it be convenient if we can tell if someone is lying? So you might think that you're good at detecting lying. After all, no one here is particularly young, so you figure you've had your life and you kind of know to detect lying. Well, let me disappoint you. You're basically at 50%. You're as good as chance at detecting lying statistically. Now, if you think you're super good at it because you're potentially trained, at a police academy to detect lying, then you're at 65%. So humans are terrible at detecting lying. We have something that's called a trust bias that actually makes us trust people more, which is crazy if you think about social media, but nonetheless, this is how we're wired. And so we're terrible at it, but machines are really good at it. So that's kind of annoying, and I'll tell you, you might see this and you think, oh, wow, AI is fantastic. Well, this is one of very few things that the machines are really good at compared to humans. Large language models aside, we'll talk about that later. So deception, turns out, and this was an undergraduate student in my lab who did this. Now she's at Carnegie Mellon as a PhD student. She took data from a court testimony. So it was a bunch of people testifying in court, and we knew the data set was labeled. So we knew if they were lying or telling the truth. So this is great because these are real data. They're high stakes data. When people are testifying in court, it's pretty high stakes, right? And she trained a supervised learning model, and it had a very high accuracy of detecting. It was like, over 85%, way better than any human at detecting lying. But okay, but that's with labeled data, right? But you don't usually have labels for whether people did or didn't lie. Then she did it in an unsupervised way, actually, and used transfer learning. And she still got 75% accuracy, which is 74, 75, which is still way better than humans. So she gave this talk at several conferences. There was a lot of interest from the police. She really did this work because we were interested in understanding when people are covering up when they're in distress. So our interest was not in detecting lying in general. Our interest was in detecting things like if you ask someone if they're feeling depressed and they're masking and don't want to tell you. And I'll tell you about that in a minute because we'll talk about mental health. But it's very interesting in general. It was kind of an interesting discovery that detecting lying is very easy for machines. That tells us something. It tells us that humans when they're lying, they do very similar, reliable things across people and across situations. So that's really interesting. It's interesting because it's a reliable behavior, it's a simple behavior, and we're still bad at it. Most things are the other way around. Most things are not simple. They vary across people and they vary across situations. And as humans, we're really much better at it than machines. So lying is just an outlier, literally, but it's an interesting one. So that's why I like to show it, because it's very counterintuitive. We as humans have all kinds of cognitive biases that make us think that we're smarter than we are. And right now we have this bias that we think that we're going to get AI to do a lot of things really easily, and we're not. So this one is easy. The rest is really hard. Like, here's an example of something that's really hard. Getting the machine, like a robot, to understand when the user is actually engaged in the interaction. So you might think this is a really easy thing, like, well, I'm looking at you and I'm talking and, you know, I seem excited, so I'm engaged in the interaction. Well, it really depends on the situation. It depends on me. Maybe I'm shy. Maybe I don't like to make eye contact. But maybe my way of displaying that I'm really interested is to glance at you occasionally. There's a lot of variety across people. And so how do we even know that someone is interested in the interaction? This is a hard thing. Consider the space of flirting and people getting together. No, this is hard. So I can tell if you're lying, if I'm a machine. I can tell if you're lying, but I cannot tell if you're interested in interacting with me. So that's an example of problems that are hard and problems that are easy. And in fact, we've done a lot of work over the past 2 decades with data with children with autism, and in particular, because autism is a really complex domain, because there's a lot of variance in behavior across individuals and also within an individual. So each person behaves very differently over time and differently from other people. So it's like the hardest machine learning problem. And that's an example where just detecting if someone is engaged in the interaction is very difficult. And it still remains an open problem. All right, so some other things you might find interesting that we have worked on in terms of human and machine interaction. We're interested in empathy, right? So we want people to be better, right? This is all about making people better. Turns out when you're empathetic to someone else, when you're compassionate, it's good for them and it's good for you. So your mental health improves, and of course you're helping them. So that's just a fact. So if you're a mercenary, be good to people because it'll be good for you. But we were interested in seeing not whether a robot can be empathetic, because you can always program a robot to say things like, oh, I'm sorry you feel that way. Oh, tell me more about it, etc. It's not hard to make robots empathetic. What's hard is to make people empathetic. So we wanted to see if we could create a robot that would make a person empathetic. That's a harder problem. We like hard problems. And so we looked at these storytelling robots and had the storytelling robots tell stories, and we wanted to see which robots would make the user, the person listening, feel most empathetic towards the robot. And we did 2 different studies. In one study, the robot was telling stories, and we found that, first of all, when the robot is talking about people, people are most empathetic. So we still like people better than robots. Relax. We still inherently prefer humans to robots, still today. But when robots are talking about robots, people are actually empathetic about robots talking about themselves. When they're talking about other robots, not so much. And this is true for people as well. First person makes us empathetic, third person, not so much. And in fact, what's interesting here is we observed the facial expressions of people, the micro expressions that are subconscious, that you're not aware of. And what people reported when they reported feeling empathy was also when they were displaying empathy unconsciously on their faces. And so we, of course, did a computational model around that because we love computational models. We want to do this automatically. We want to be able to predict what behavior in the robot will make the person empathetic. And so we built a machine learning model, tried different things, found that the XBoost part was the best. This is a whole thing we can talk about separately. But anyway, this is like, 69, 75%. That's pretty good. So basically, we can automatically now, in some sense, we can endow robots with behaviors that will make people more empathetic. This is pretty cool. People have trouble making other people empathetic. Maybe we'll need machines to do it. Another set of studies we did is we looked at what other kinds of things evoke empathy in people, and we looked at a service robot that is stuck in its task. And we looked at a robot that is neutral, that just explains, like, I have detected physical contact with a wall, my functionality is damaged, or, oh, I usually see pretty well, but now the darkness has overtaken me. Or these scripts are written by my students. Or oh, I'm afraid I might have come apart and I'll need to be fixed and it's so scary. And so which one would evoke the most empathy? So it turns out sad robots reliably make people feel sorry for them, which I found kind of interesting because as a roboticist, I find that annoying. But, you know, I'm probably not typical. So what this tells us is that when it comes to basic kinds of behaviors, people feel empathetic similarly to robots that they do to people up to a point. A robot cannot get away with being dysfunctional as much as a human can. So you expect a robot to be able to do what it does, and if it's sad and sappy and apologetic, you'll put up with it, but to a point. And then you're done. Like, okay, you're not doing your job. So why is this important? It's important, one, because it tells us about how we might change our behavior, but two, it tells us how to design machines that get the responses that we want. Speaking of responses, we're very interested in group interactions. Not everything is one-on-one. So we've done work with robots mediating groups. And you might wonder, why do we care that a robot should mediate groups? Well, one of the reasons that we care is we're interested in support groups. So during the pandemic, of course, mental health, went into the toilet. And the best way, in many ways, for people to feel better is to talk to other people. And so we were interested in creating a agent and robot mediated support groups because there are not enough humans to serve as support group mediators. Why? Because it's an extremely depressive, draining work. Okay? And there's a great need for support groups. And so we actually have a National Science Foundation grant to help us develop these physically embodied mediators that could be in situ, but they can also be over Zoom. So you might wonder, well, if it's over Zoom, why isn't it an artificial agent? Because it doesn't work as well. Even over Zoom, you feel better when you're supported by a robot over Zoom than by a screen over Zoom. So that's my point from earlier in the talk. So one of my earlier students did this beautiful work where she modeled group interactions. And this is the same as stuff from organizational theory. It actually echoes organizational theory. So the robot was just paying attention to who was talking and for how long and what he would do. He didn't understand anything about what they were saying. This was like 7 years ago. So no real-time speech understanding. But what he would do is he would say, if one person is talking a lot and the other one is not saying much, he would say, oh, this is great, thank you. Now, let's hear from you. You haven't said anything. So that's all it did. And the groups overall ended up preferring the interaction when everybody got to talk. There's much stronger group cohesion. And then the more interesting thing is that we brought these people who were strangers before the interaction. We brought them back 2 weeks later. So they're strangers still, but now they've interacted once before. We bring them back 2 weeks later, put them in the same room, and now we give them a task, which is a competitive task. So it's a zero-sum game. So they really need to compete. And they're still nicer to one another. They don't actually want to compete because they had this one interaction in which the robot helped them get along. On the other hand, if you set up the interaction to be competitive to begin with, so you take a group of strangers and you optimize who can do it faster, who can do it the fastest, who's going to win. What happens is you get a competition, someone wins, they don't particularly like each other, you bring them back the next time and you get more cutthroat competition. This echoes organizational therapy, right? If you get teams and you set it up as a competition within a team, you'll get a winner, but it's not a good team. So it was very interesting stuff, but we're very interested in it for support groups because we're interested in disclosure and trust. Back to the deception bit, we want people in a support group to feel comfortable enough to tell the truth so that they can feel better. Of course, you have to do this privately. You can't disclose any of the information. I mentioned this because this is an ACM lecture. So this is an ACM Grand Challenge Award that a student of mine got for a turn-taking model. And here's just a simple thing. Most machine learning models for turn-taking, they're based on speech. So I'm talking, and the model is predicting when I'll stop talking, based on what I'm saying and also based on some auditory features, right? Well, my student beat every single one of these models just by looking at eye gaze. So what does that say? That basically says that we are multimodal creatures. I'm signaling in many ways. I'm moving, I'm talking, I'm looking. All these signals are happening at the same time. And machines have to pick up on all these signals at the same time. If they only take my speech, that's not enough information, right? So it was a pretty major accomplishment just by having one basically simple idea. All right, so let's talk very briefly about learning. Well, there's been learning throughout, as you saw. So remember I told you about mixed reality and virtual reality. So this is kind of what it looks like when we have students grabbing pieces of code or math in thin air they're seeing this augmented reality through their tablet, and they're just moving things around. But what's interesting is by having them do this physically, by moving their body and reaching and grasping, they learn things better and they retain them better. They experiment more. That's what we call kinesthetic curiosity. So if I'm teaching you to code and you're sitting in front of a screen, which is how 99.9% of coding is learned, you're going to learn less, in part because you're not going to be willing to try and fail. But if you're moving around, if you're building code blocks by pulling things, the fact that you're doing physically makes you experiment more, you learn more, and you're a better coder. So this is a very powerful result that comes out of the fact that we can get them to move around. Just to move around, and the fact that they can do that with augmented reality. Now, of course, I don't know how you do a classroom full of 20 kids moving around, but they like it. We tried it. They thought it was just fantastic. So this is something about how the brain works, how we learn, and why movement is important. Another thing that one of my students is doing, she's just graduating now with a PhD, but remember the one with the babies? Now she's looking at the interaction data between not just the baby and the robot, but the baby and the caregiver. And there's a give and take and give and take. And that's it's a complex system. It's a time series of interactions. And being able to tell when something has gone off a little bit. So the mom does something, if the baby doesn't respond just right, and the mom does something to compensate, and then the baby may or may not respond, and this can spiral out. So often detecting these small anomalies can be a sign of toxic stress early on. So diagnosing these things early from data, from vision and facial expressions can be a powerful way to help early child development. But it's hard because all of these data sets are really noisy, and there's a lot of missing data. You know, babies cry, they look away, they tear the sensor off, they do all kinds of things. And so there's a whole subfield of machine learning that deals with things like what happens when you're missing data and imputing data, because you can't just interpolate. People who are in engineering think that you could just interpolate. Oh, the signal looks like this, and then it looks like this, so we'll just say that it looks like this in between. This is human behavior. You can't make these assumptions. If I go away and come back, you don't know what I did. You can't just say, oh, she stayed here the whole time. We're just interpolating, right? So it's very complex to deal with missing data or noisy data. The other thing is model selection. So usually what we do when we're trying to understand human behavior is we have a model and we're trying to basically classify, right? Like, oh, well, my model predicts that this is what's happening. Well, your model is going to necessarily be only good during a certain behavioral regime. And for different kinds of behaviors, different models are better. And so that's difficult because what that says is you need heterogeneous ways of modeling human behavior. You can't just use one model. And so Lauren has some very beautiful work to talk about basically optimal models and the fact that you need different kinds of models. And she herself is doing everything from complex systems modeling, which goes back to the 50s, all the way to deep learning. And you know, sometimes the complex system stuff is the best. Even though it's from the 50s, it's still the best for some things. So that also tells us we should not be obsessed with the latest fad, which we as humans love to do, especially in AI. Here's a very big study that we did. I'm just going to play this briefly.
Meet Adrian, age 6, and his robot friend, Kiwi.
You are doing an amazing job.
On this weekend morning, they've settled in to play some games, along with Big Brother Darren. Adrian is on the autism spectrum, and Kiwi is no toy. It's a socially assistive robot.
You are doing really great. Keep up the good work.
So this is a part of the video that the National Science Foundation put together based on a work that we did with a few other institutions as a part of a big National Science Foundation grant that we had. This is a 5-year grant that we stretched out to 9 years. But we were the first people, in collaboration with Yale University, to deploy these robots in the homes of families with children with autism for a month at a time, collect data of real interactions, and then analyze those data and fit machine learning models to be able to change the behavior of the learner, of the child, both social behavior and learning behavior. And so we could do things like personalize the level of challenge and the level of feedback. We did mixtures of deep learning and reinforcement learning in order to basically do very individualized challenges for each child, because in autism, it's about every child. Every child is different. Of course, in humanity, every person is different. So autism is just an example of the hardest version of that problem. If we can solve that one, we can solve everything else. And so just look, if you look up socially assisted robotics in Science Nation, you can see this whole video. And it's just really, it's a really nice demonstration of a group and team effort of what it takes. But the main thing was, you can give a kid a tablet and they can learn from a tablet, but they don't learn any social skills at all. And when they get stuck, then there's nothing to help them, right? So the automated tutoring systems will give you an easier problem or a harder problem, but that's about it. Here, what the robot would do, it would say things like, oh, I like it when you look at me when you're happy, right? So now they're learning a social skill as well. Or if the robot is talking and the child starts talking, the robot stops talking, and the kid doesn't like that because they want to listen to the robots. And they stop talking, then the robot starts talking, the kid starts talking and interrupting, the robot stops. The child learns that, okay, if I want the robot to keep talking, I need to stop talking. So they learn to take turns because they're motivated to hear the robot. So there are a lot of social interactions that they learn. And this is why kids need to be in school with other kids, because like, you know what social learning suffered when kids would not being able to be around other kids. And now, of course, we have to protect them, right? But the point is, this social behavior training is necessary. And for some children, more training is necessary. And if they're not getting the training from other kids, this is a path that you can get them to learn. And then what's great is other kids also like the robot. So now you can get group interactions around the robot. So there's a lot of potential there. That's one of the areas that people are looking at monetizing, obviously. This is fun for like older generations. We were interested in keeping people from sitting too much. This is not an older person. This is my former student, Kate Swift's thong. All the pictures are largely of unless we have disclosure from people and allowing to show them, the pictures are my students. So we actually, Kate put together the system where we took it into people's homes, elderly people who lived alone. We gave them a little chair pad that they would sit on that could tell if they're sitting or not. And then we connected it to a robot right next to them. And if they sat for more than 30 minutes, the robot would say something like, oh, I think you shouldn't sit so long. Come on, let's get up. If you get up, I'll tell you a joke. Or if you get up, we can dance together. And very quickly, people changed their behavior. Not just that they would get up when the robot prodded them. Remember, I told you that's nagging. No, what people learned was that they would anticipate before the robot would nag them, and they would get up. And then the robot would say, oh, nice work. You get 2 jokes. And so they really learned to anticipate. So they changed their behavior. It was super effective. And then after 2 weeks, we had to take the robot back because, we don't have them. We don't sell them. We don't give them away. And then you know what happened. Everybody just went back to sitting a lot. They missed the robot and they went back. So they didn't really change their habit. They just changed their social behavior. So that's interesting. It tells us that people can very effectively change their behavior with a robot companion, but the people are not willing to change their behavior on their own. So it's interesting. Just one of our many studies. We did some work with Alzheimer's patients. This was a while ago. We actually got Alzheimer's patients to learn a new game and a musical thing. And it's very hard. Alzheimer's, of course, just progresses, but at least it improves their quality of life. I will skip this because it's a relatively old work. So in general, we need to develop these systems that use multimodal modeling of the interaction in order to adapt to each user. I want to show you this video. This is a 3-year-old with special needs. This was recorded 4 years before the pandemic. So I just want you to see this. This is a child interacting with a robot in real time. No one's pulling any strings behind the curtain. This is just a real-time interaction where the child has to do a game and behave socially relative to the robot. And the robot will give her praise and will advance the game when the child does the right things. This is all happening in real time. There's no magic. This is a 3-year-old. And so let's see what happens. So it's a counting game. She counts, the robot counts. If she looks at the robot nods and advances the game. See, the eye gaze, the social, the reach, the speech, everything happens in real time and everything is progressing. If she doesn't look or she doesn't say the right thing, then the robot prompts her. I just want to say, this was 3 years before the pandemic. So why didn't all children have a robot like this to help them when they were stuck at home? But they didn't. You know why? Because no one's investing in this. No one's investing in this stuff. This is going to be on the web, so you don't have to record it all over there. This is all going to be in the YouTube talk. So, where's the investment? Where is the investment in technologies for child development? Because there's a lot of low-hanging fruit, but that's not what people are investing in. Just want to point that out. So right now, this is what we're doing for closing. We're interested in mental health. Mental health is the biggest pandemic right now. Anywhere between 65 to 85% of college students are suffering from anxiety and depression. We're looking for we're developing a low-cost, accessible, soft robot that can actually help students with mindfulness, biofeedback, breathing exercises, coping strategies. Also working with ADHD, autism as well. So there's just a lot of people that can be helped across the age and ability spectrum. And of course, we're looking at some of the latest technologies like natural language dialogue using large language models. So now you can have ChatGPT. You're just waiting for me to say that, weren't you? Of course. So yes, there's ChatGPT. And it's just like talking to a human. And you can, if you say certain things, maybe into GPT-3, maybe not into ChatGPT, it sounds like you're talking to a therapist. But is it dependable? Is it reliable? Is it going to go off the rails? With what probability? This is not known, right? So we have this tremendous ability now to generate text and dialogue using these models, but it is not well understood how well it can be kept on a rail. So that's a huge amount of investment is going into that. We're not limited to that. So in summary, so that I wrap up on time, hopefully I have convinced you that well-designed human-machine interaction, and in particular human-robot interaction, can make us better. There's a lot of evidence across the field over the last 20 years of improved health outcomes, more social engagement, more empathy, less selfishness, improved learning and training across the age span through human-robot interaction. But this is only going to happen if we work on real-world problems, if we get out of the labs, if we collect real data, things like that. So I get disappointed when I see students who want to go and just download a bunch of data sets from the web, use top 5 machine learning tools, and print out a chart about what happened. That's not interesting. That's not going to change the world. It may be 90% of published papers today in machine learning, but it's not interesting. The interesting stuff is taking a real problem, like how can I understand if the kid with autism is actually paying attention to me so I can help them? Now that's a hard problem. Can I tell if you're lying? Not a hard problem. Not an interesting problem, apparently. So the thing that I always tell young people, but really all people, is just don't get distracted by all of this talk about what AI can do. Pick a really interesting problem, and it will explain to you very quickly what AI can and cannot do, because most interesting problems are really hard and they're wide open right now. And I just wish more people would work on them. So on that note, I want to thank my students. These are the people who make it all happen. And thanks for having me. All right, let's have all the questions now. You have to have questions. Oh, yes, please.
When you were looking at maybe taking the ball and the robot was demonstrating how to do something, the thought occurred to me that your robot is a device that is controlled by a human indirectly. It was programmed, built by a human. So what is the real difference between a robot being programmed and electronic versus something, a puppet with strings doing the same thing, controlled by a human behind a screen? Isn't that the same thing, just scaled up in some way?
Have you ever programmed a robot?
Second?
Have you ever programmed a robot?
Not really, no.
Yeah, well, that's the difference. When you're writing a computer program, eventually, when it works, when it's debugged and it runs, it just runs. And then it runs whatever data you put in, it does the right thing. That's not how it works with robots. Robots take sensory data from the real world through a sensor. The sensor could be really simple, like a switch, but mostly it's something complex, like a visual sensor, auditory sensor, right? So there's a lot of uncertainty for robots. So it's not at all predictable. The robot is trying to make a decision based on the information it has. It is making a decision, not the person. The best that the programmer can do is usually put some kind of a probabilistic model of what the action should be. But we do not know. We can only predict that with some probability, this is what it may be seeing, and therefore this is what the action may be. But the reason that robotics is so much harder than programming something on the screen is the uncertainty.
Well, I understand what you're saying there, but isn't it just sort of a scaled up problem? Isn't there some continuum between a puppet and a robot?
Well, I'll tell you how it is a continuum. We have no idea how the human brain works, and therefore we don't really understand how we puppeteer things when we're puppeteering. To that extent, yes. So the point is, no, it is not, because you can never, just like, so it's non-deterministic in a way. You cannot know for a robot exactly how it will perceive the world around it and how it'll respond. It'll respond within the options that you have given it when you programmed it, but you cannot predict exactly what its next action will be. That's both good and bad, but that's why it's hard. The uncertainty is huge, and now people are trying to do, I mean, you know, just to give you like a very, very basic example, that's the reason why there's the liability around autonomous driving. Because if autonomous driving were fully deterministic, then we'd be done, right? Wouldn't we? But it's not, and it never will be. And it'll never be for two reasons. One, because perception will never be absolutely certain. It cannot be, because sensors are always noisy and flawed and partial, because that's just physics. It's physics, and you can't go around physics. That's why robotics is hard and computing is less hard. Second, because of people. People are totally unpredictable. Even if you had a fully deterministic car, which we never will, you will never have a fully deterministic human. The human can do a crazy thing and crash, like the human cutting across can still cause a car crash. People do it all the time. So that's why it's not, no, it's not like puppeteering. It's nothing like puppeteering. Yes?
So I have a question about where's the robot's primary sensor coming from? Is it eye detection? Is it facial detection? And where is the what's the person react most to? Is it facial? You know.
Yes, I think I understand what you're saying. So, our robots in general have a collection of sensors, right? So they usually have cameras that they're looking at the human with, because the human is the thing that they care most about. But if they're mobile robots, if we're driving around like the ones that you saw on the floor, they also have other sensors. They might have, for example, I showed you in the augmented reality, the rays that were coming out. Those were sonar sensors that are coming out of the robot that you can't see, but the robot is using in order to do navigation. They always have microphones, right? So they're collecting audio as well. So that's multi-modal sensing. So that's what the robot is perceiving, right? Now, what is the human looking at or attending to? That's the hard question.
Reacting best to?
Well, there's no simple answer to that. It depends on the human. It depends on the task. It depends on the interaction. It literally changes. Like if I put you together in a room with my robot for 45 minutes, the way you respond to the robot in the first 5, 10, 15 to 45 changes.
But you know,
right?
I could imagine, my mother always had Alexa, and Alexa, she would talk to it and all that. And,
sure.
She had that conversation. She didn't have very good eyes, and she was not very mobile.
Mm-hmm.
But I can imagine that the next level interaction, if she had a facial expression to talk to.
Right,
you know,
that exists.
This is disemboweled voice off on the side.
Right.
But if she could look at something can look back at her, I think that would
right.
be more of a...
So that already exists. There are plenty of agents that are just faces displayed on the screen. In fact, there's an entire field of research called affective computing, which is all about how we display emotion and how we perceive emotion, right? But those are not robots necessarily. Right? Although they could be. You could have a robot that has a screen face. We generally do that because having a screen face is a lot smarter than having a face that's actuated. Because if you have an actuated face and it has like an eyelid and then it droops and then the robot looks drunk and many reasons.
The robot that tells you're lying, what do they use? Is it
It's using a camera? Yeah, so it's using a camera. This is just video.
I'd be wearing sunglasses when I talk to the robot.
Yeah, so that's actually a great question, because that gets at the question of how the model is trained. So the model that we were looking at was looking at data from people doing testimony in court. So they were not wearing shades, because you cannot wear shades in court. It's not even allowed. Okay? The same way that you can't wear a hat in court. But that means that the model could be broken with people wearing shades. But you don't get to wear shades when you're testifying to the police either. So.
Well, next time I'm talking to a robot, I'm wearing my shades.
See, there you go. And that's true, and that's a bigger problem. So there were, even outside of robotics, there were a lot of problems with AI because it was trained, let's say, mostly on Caucasian people and then couldn't recognize other races. It's getting better now, but like there were a bunch of scandals like 5 years ago about things that machines were labeling inappropriately. Yes. Yeah. Who? Okay. Yeah. Sure. Yeah. Didn't see you. Go ahead.
Thank you very much for a great presentation. First of all,
Thank you.
I learned a lot. You've asked the question, how come we don't have those robots at home before pandemic, and people can actually have the investment in that. So my question is, imagine we had it. Imagine every home actually has one of those robots and so on. So are we talking about the transformations of businesses, kindergartens going away and gradually schools going away? Because again, if parents can have very sophisticated educational tools at home, like robots that they know exactly what their kids are learning and so on, and are in a very safe environment, et cetera, and are at the same time socially being interacted with. So why should they take their kids to schools and so on? So there are a lot of other ramifications associated with that.
There's a really, really, really large gap between what's happening now, which are kids staring at YouTube, and having a robot that could give you maybe an hour or two of entertainment per day that would be developmentally better than staring at videos on the computer, and replacing all education and social interaction. So I think that is not a reasonable slippery slope argument, because we're nowhere near being able to understand how we can scale this up. What I'm trying to get at is that during the pandemic, millions of parents had children at home that they didn't know how to interact with because either they were working themselves remotely, and now what's happening with the kids? So all the kids were just staring at screens. So they were not getting any social interaction, and they were not getting cognitive development. The idea here is that you're going to fill some hours of the day. That's the same as, for example, the autism argument in the limit. If for every child with autism we had a PhD level therapist that was there with them alongside the parents, and the parents sometimes have to sleep and go to the bathroom and do work, but the rest of the time, right, you've got this therapist there all the time. Well, it still doesn't generalize, but it's something. Well, no one has that, right? Or okay, I know one billionaire who has that, but aside from that, who has got 5 kids on the spectrum. So we all know who that is. So other than that, who is going to have that? So the idea is that there's a gap in care. There's a gap between what kids need, what people need, and what they get. And the idea with technology is to make that gap a little bit smaller. You're not bridging the whole gap, but you're making it smaller. That's the idea. So what I'm trying to say is children are watching millions of hours of screen time that is not developmental. And they're missing opportunities for social development and cognitive development. And the idea is to just address that a little bit. No, but you're not suddenly making people obsolete. That is not the idea. Does that help?
It's only a matter of time, though.
I do not think that at all.
It's just a matter of how.
I really, really don't think that, because I think that there are going to be really serious ramifications in the mental health and developmental health of children who were in their critical developmental stages during quarantine. Yeah. And it's no one's fault, because people had to be protected, excuse me. But, for example, the babies that didn't get to see facial expressions because of masks. Yes, saved their lives, but they were not getting the development they needed. So what's happening right now with screens, and I think we should put blame where the blame needs to go. The blame needs to go to social media, which is doing social comparison and depressing kids, and there are causal studies in abundance to show that, and the fact that kids are getting too much screen time and not enough eye-to-eye time. There are also studies that show, incidentally, that when you're talking to a human on the phone and you're hearing the nuances of the human voice, your mental health is better than when you're texting, because you're not hearing the human voice. You're not getting the nuances. You're not getting connection. Emojis are even better than just texting. How pathetic is that? Studies have shown this. These are actual therapists, actual psychologists that showed this. So I am by no means saying that we should take people out of the loop and replace them with screens. Screens are bad. Screens exclusively are bad, and they're doing terrible things. And if the measures of the mental health crisis that we're seeing at a global level right now are not an indication to people, maybe they should wake up. But how do we address the gap, right? Because also, who is going to be with these children? And unless society completely turns on its head, who is going to be with the kids, right? So the idea is you're not going to be able to eliminate all screens, so can you, or eliminate all technology? How do you develop technology that is good for people? That was the theme of my talk, right? Not replacing people. People are wonderful when they're wonderful, but not when they are underpaid, overworked, and suffering. Sorry, somebody else had a question. Yes. Oh, well, she was before you, I think. Now, she ceded her turn. Then you're next, but she did go first.
Thank you. Is this thing on?
I can hear you. Just yell.
Okay, I'll just pretend like I'm speaking into this. Well, first of all, I am very happy to see this research, and I think it's wonderful. I'm a college student at Cal State Fullerton studying computer science and child development.
Yay!
So hearing about this is really encouraging, and it gives me a lot of good ideas on what to look for and work on moving forward as I enter the workforce. I like what you mentioned about personalized self-regulation during learning. I think that's really important for children to learn so that they would be able to self-regulate while in society and interacting with others. I know that you mentioned that we need more investment in child development technology. What do you think are some of the reasons why we're lacking in that funding, and how do you think we can change that? It's kind of a long-winded question, so if you want me to
No,
repeat,
I agree with all the points. I'm just trying to see how to say this without, I have trouble not being blunt. We do not value family and education in this country, and that's why. So, and let me say this from a data-driven perspective. So I'm not talking about this as like my personal perspective. Studies have shown that countries that value educators have better outcomes. So countries that invest much less in education but value education, and they, for example, think of educators as people who are high status in society. This is not the case in this country. Educators are very low status. We professors are sort of okay, but not that cool. But, you know, K-12 educators, no one cares about them. They don't get paid enough. Oh, they get tenure, but barely. And that reflects itself in outcomes. And so countries, this is very clear. Like if you look at countries, and their international testing that happens regularly across countries, and the U.S. scores very badly. So our students generally score very badly. We're like, you know, 25th or something of the developed world or less, or maybe 40 or something. It's awful. But we're very confident. Our students are very confident and terribly performing relative to the other countries. And you've got smaller, less resourced countries where students perform really well, even though per capita investment is much lower. But the societal value of being an educator is high, which means children are incentivized to pay attention and to learn. So that's one answer. So no wonder that in a society where we don't value education, we don't invest in it. You know, when we're choosing what to invest in, this is not a priority. For example, it's been known for decades that preschool is fundamental to outcomes in life. Yet we don't have preschool, unless you can afford it. So it's things like that. So, you know, and these are data. Again, these are not philosophical or political statements on my part. I'm merely citing data. If data showed, for example, that it was better to keep your kid at home and not put him in preschool, I would tell you that, because I'm just a scientist quoting you studies. So.
Okay, well, thank you for your answer. It's good to know kind of all aspects about making this work, including why we're not receiving funding, so that we can be prepared to, you know, talk about why it's important.
Push it. You can change things. That's the beautiful thing about the next generation. You guys should go and change things. We researchers get data and information, and you young people have to go make the change. I'm a huge optimist because I really am impressed by the young generation. I mean, I work with young people as my job. It's the best job in the world is working with young people. It's true. You guys are going to go and do amazing things, and please do it better than we did.
I'm excited. Thank you.
Yes, please, your turn.
It sounds to me like this whole robotics thing is a fairly capital-intensive and difficult thing to do. If you look at the history of innovation, I mean, I look at people like Jones and Wozniak building an Apple II in their garage. I look at Hewlett and Packard building an oscilloscope in their garage. Is there any tinker, inventor community that you know of in this robotics business?
So we're past that. You are past in robotics, in electronics, although there's kind of a new open source thing for transistors right now. But in all of these things, we're past that. There's a very strong argument that in many fields of knowledge, kind of the low-hanging fruit has been picked. So as humanity, we have made massive strides, but that means that the problems we're looking at now are more complex. So you cannot just tinker in your basement and create a robot that will do the really complex things. You cannot tinker in your basement and solve quantum right now. You cannot tinker in your basement and do nano. We have done many of the things that we could do, but now the problems we're looking at are harder. And so, and that's not to say that they were easy then. Those people were amazing innovators for the age that they were in. You know, just like Galileo was and Ada Lovelace. But now, you are not going to build that amazing robot in your basement. Just like, you know, there's some really fundamental questions about the scale of investment. Like large language models right now, the things that sound like people, overly confident and often inaccurate, only extremely well-resourced companies can make that happen because they're the only ones that have the resources, right? So no, you can't do that in your basement. Just can't. That's the reality. Now, I think young people should tinker in wherever they are as much as possible, especially the physical stuff, because it gets your brain flowing and that sets you up to do interesting things later. But unfortunately, resources are quite important to solving a lot of these problems.
Well, thank you for your talk. I liked it. So a couple of applications I was thinking while you were presenting, that would SAR be used in enhancing or even starting some habitual activities in kids? For example, book reading or painting or like playing some musical instruments or so. Because I think this is something that could even bring more value, right? And then I have a second question, but I would let you answer this first.
Absolutely. Don't take his microphone away. No, I love it. I completely agree with you. In fact, I didn't talk about this a lot, but you know, the study I showed you about old people sitting in the chair, but not like, you know, getting up in less than 30 minutes. The whole point was to use the robot to be the stimulus and the reward to form a habit. So your point about, you know, getting kids motivated to, you know, whatever, read more or do these healthy habits or smart habits, that's exactly the point. That's the idea, this social pressure that, you know, you will do things like, okay, I walk every morning and I have a neighbor with my dog. So my dog kind of is my excuse to walk. So I have my motivation. And I have a neighbor who always wants to walk with me. She's like, I don't walk unless I walk with you. So you have to tell me. So I basically get her to walk. It's the social pressure. So she has a habit. The habit is to walk with me. My habit is to walk with my dog. So, you know, if you have a robot that says, hey, now is the time to, you know, read out loud to me, right? These are the kinds of things that we could do because the robot is the buddy for the child. And that's not to say that the child shouldn't have a human buddy. Absolutely. But it's going to be kind of hard to find a human buddy who's going to want you to read to them in 2023. So, you know, I agree with you. I think it's a really good direction to go in.
Yeah, and then the follow-up question was that you mentioned in the beginning measurables, right? So what are the measurable metrics or merits for SARS, for example?
Okay, so first of all, in all of these studies, whenever we do the studies, we always have outcome measures, right? So whenever you're doing a human subject study, you have to have some kind of outcome measure, right? So for example, when we were doing let's pick any of the study. If we're doing like getting people to not sit too long, what we wanted to know was what is the distribution of how long they sat over time? How did that change? Did it get, you know, did their time sitting get shorter over the period that they were interacting with the robot? Also, we do things like how much eye contact do they make with the robot? How much verbalization do they do? Do they talk to the robot? Do they smile? Facial expressions. We're always collecting data on facial expressions. We have to get human subjects approval every time for this kind of stuff. And we don't share these data, but we're always evaluating, right? So we want to be able to report in all of our papers things like, you know, your sitting time was cut by 50%. And our measure for significant improvement, right? So you do things like power analysis, statistical significance, right? So these are standard measures. The important thing is that typically in social robotics, there are no such measures, right? You say things like, you know, oh, people like this robot. Look, they're smiling, right? You know, we want to say things like, I mean, ultimately, I like to be related to health, right? I want to tell you the grade went up by a full grade level, or I want to say your blood pressure went down by this much, right? So we're looking at real health or behavioral outcomes. It's hard. That's what makes it hard.
Yeah.
But thanks for asking, because I needed to cover that.
Yes.
So I have two quick questions. The first one is a little bit philosophical, something related to the other gentleman asked, is that the criteria of the robots you're training, so
Okay.
the unselfishness and the apathy, those are very vague concepts. But in order to implement that, how do you kind of define evil or good? Okay, this is the most philosophical, how you build the rules in. Secondly,
Yeah.
is that we are very individualism and also the diversity. And if I like a guy more active, how you define a robot for me if I get some sick? So how you implement that, how you
Yeah.
allow the user to select those things?
So these are great questions. And I should have made this more clear, but I should have made all the things more clear. So first of all, how do we, if we take a phenomenon like empathy, how do we actually go about modeling it? So the very first thing that we do is we will learn everything that is known in behavioral science about it, right? So my students don't just read computer science papers, they read a lot of social science. Because, for example, one of our past works was modeling personality and having a robot be an extroverted robot for an extroverted user, because that makes the user more motivated, right? So what does it mean to be extroverted? Well, we went to, we looked at the Big Five questionnaire for personality, we looked at the scale, so we can measure how we define a social phenomenon. So empathy, there are many books on empathy. I would recommend actually Baron Cohen, who's a really well-known researcher on empathy. And lack of empathy and what that means in various ways. And so we read from social science and then we model from there. So for example, again, let me use personality because personality is such an easy way to describe it. So if you look at how extroversion is displayed, some features of extroversion are, people who are extroverted tend to stand closer to you. This is before the pandemic. They tend to stand closer, they tend to gesticulate more, they tend to say more words per unit time, more words per minute, and their speech tends to be slightly higher pitched, regardless of gender, just from baseline, okay? So I can build a robot with those features. Those are all measurable features. So if you ask me, how do you create an extroverted robot? That's how. I look in social science, I see what it means for a human to be extroverted, and I look at that and see how I can put it in a robot in computational ways. So for example, when we did surprise, right? How do we model surprise for the robot relative to the baby? We looked at the human model of surprise, the one I mentioned, Laurent, right? That predicts where you will look. What will surprise you most? So that's done with human visual data, right? So some models are rule-based models, like this business of gesticulating and words per minute. Some models are data-driven models, like where you look, right? That's how we model social phenomena. Okay, now, how do we personalize? You're exactly right. Every person is different. In fact, you are different from day to day within a thing, like you're more tired now than at the beginning of the talk, but maybe you like me a little bit more now than you did at the beginning of the talk, or less. Could be either one. So things change all the time. So the whole point of these technologies is they adapt to the user. Probably the most popular model of adaptation like that is reinforcement learning. That's kind of like if you think about how machine learning is done, if you want to adapt over time, it's usually some type of reinforcement learning. There are many types, but some type of reinforcement learning. So often there's kind of a reinforcement learning mechanism. Now that is just one kind of learning that's happening. The system may at the same time be using a model like to detect, like let's say I want to detect if you're happy or not. For that I might have a model that I learned from data, right, where I'm classifying all the time. What is that facial expression that you have right now? You're kind of smiling, but you're kind of skeptical. So, I classify that, right? And now you've changed your expression. Oh, now you're smiling, right? And then at the same time, I'm running reinforcement learning because I want to maximize the smiling. So, okay, yeah, you're smiling. So what did I do? Because you smiled. Whatever it is that I did and now you smiled, I should do more of that. So you see what I mean? There are multiple types of learning going on at all times, but to personalize to the user. And that's really interesting because if you look at, and I want to throw this out as an interesting point of thought for you as you eventually go home. Most science studies don't allow you to do learning because they want to be fixed. So if you do a study in medicine, the thing that you're doing has to be controlled. It's a controlled variable. Your system cannot change. But the whole point of technology, intelligence technology, is that it changes and adapts to the user. So that's really interesting because when you're doing a study, like if I'm doing a study where I'm going to have the robot adapt to the student to make the student less stressed, how do I evaluate that? One thing works for one student today, this other thing works for another student another day. It's just like health, right? And this is a thing that's happening in health as well, that you can't just run studies where you take 300 people and you give them the same thing and see what happens. I mean, that works for certain medications, but it doesn't work for behavioral things. And so the whole science of studying behavior, with or without machines, with or without robots, is also shifting right now. There's just a lot of interesting stuff going on. It's a fun time to be alive, except it's a mess.
You need to write a big disclaimer when you sell this robot. Any of personality shift has nothing to do with my robot.
That's right. If you don't like the robot, it's your fault. No returns. No, and in fact, the flip side of that, sorry, I'll just say this other thing. People are often worried about people actually really liking the robot. And then what happens when the robot eventually breaks? Because, it's going to break eventually. Oh, but then you don't want a new one. This is already happening with the Roombas. The Roomba vacuum cleaner, right? A very simple robot. It has no personality. People treat it like a dog. They ascribe all kinds of things like, oh, it knows me and mine is shy. It's happy today, right? None of these things are true. And then when it breaks, eventually, because it's not, it's anywhere between $250 and $1,000, it eventually is going to break. The company sends you a new one. People hate that. They want theirs back.
We'll do the last two questions.
And the guy with the hoodie who keeps recording.
Excellent talk. Thank you.
Thank you.
Wonderful. Very interesting. I wonder, in your advanced robotic studies with the graduate team, have there been any studies around how to model intuition into a robot?
So there are people who have thought about this. It all boils down to how do you define intuition? What is intuition, right? So, in a robot, how do you represent knowledge, right? You can have rules. Rule-based systems used to be how things were done. Until recently, there were decision trees, right? Then there are policies, right? State action pairings. And now increasingly it's these models, right? Where you have this big statistical data-driven model or a neural network, and you put some input in and something comes out and nobody understands what's going on in the middle. And so what's intuition then? These are different representations. AI is all about representation, right? You represent knowledge and information in some way. So you could choose one of those and call it intuition, right? I mean, what is intuition? Right? What is even intuition for us? For us, maybe intuition is just the thing we don't understand. Like, it's a kind of reasoning we don't really understand. It's like a gut feeling. What is that, right? So, yeah, it could be intuition. Depends how you label it.
Thank you.
You have to let the guy with the hoodie also speak, because I want to know what, like, the secret agenda is there. Yes, please, please.
So I had a question around using the robots to elicit change behavior in humans.
Yeah.
You left the robot with the child or whatever for a few weeks, and then you took it away, and it helped make changes, but then they reverted.
Mm-hmm.
Is that not to be expected? Because my understanding is we need 30 to 60 days of repetitive behavior in order to actually create a change.
Yeah. So just to clarify, the study that we did with the elderly, it was 2 weeks. We absolutely expected them to revert. We were interested to see if the robot was able to make them change the behavior, and it was. With the kids, we had the robot in their home for a month. And what we were measuring is change in social behavior, pre-post, and then a month later, and also change in improvement in cognition. And in that case, a month later, post-study, the changes were still retained. So you're absolutely right. You do need a month. Sometimes you need longer than a month to observe anything. So I agree with you. And that's one of the really hard things is it's very hard to deploy technology in the home. Like, for example, with our studies with kids with autism, one family did not have air conditioning because, by the way, we did not choose to just deploy in Beverly Hills. We deployed around USC with low-income participants as well. And one family didn't have air conditioning and got to 100 degrees outside, so it got to 100 degrees in their apartment, and then the robot overheated, right? So who anticipates stuff like this? It's not a commercial product, and even if it were, probably would have overheated. So the point is it's just so hard to run these studies. So I would love, we're constantly submitting proposals to run bigger studies with more people and longer time, but it's just really, this is what I mean, but there's not enough funding. It's just not a thing that's prioritized. Like, there's a ton of money going into certain kinds of research and not a ton of money going into this yet. Someday, but it's a priority. unfortunately.
Do you want me to interview the other
Well, I'm not prioritizing him, but I just want to hear because, you know.
Does the mic even work, or it's
You're probably not. It's a placebo. It's okay.
Okay. So yeah, want to say, loved your talk. Wish I had you as an instructor or professor back in
Oh,
the day.
thank you.
Yeah, so.
You can at USC. I'm over there.
Yeah, maybe I'll sit in one of the classes and see you just hop in. But you spoke about like instilling engagement and some of the models that you had doing that. Seems like you got that down to the nail with babies. The whole like coaching babies with the Bayesian surprise that you had going on. Curious though, did you also like do that study against like autistic babies? I know you mentioned like autism in children that are like 3 years of age and above.
Yeah,
Does
that's
that same kind of model or approach still work?
That's a really good question. And one confound there is that these babies were between 3 and 9 months. I think the one that you saw was like 6 months. So babies who are on the spectrum, but there's no such thing as babies on the spectrum because you don't know that someone has autism until they're about 2 years old. So usually the diagnosis happens at around 2. And there are various reasons why. It turns out there's a really beautiful study actually that was used to debunk all the ridiculous concerns about vaccines and autism, which are completely untrue. So for children who are diagnosed with autism, there was a very large study where they looked at videos from their first birthday. And if a scientist analyzed the video of a baby at their first birthday, and they didn't know whether the babies did or didn't have autism later, they just analyzed them and said, we think these do and these don't. You can actually determine some fair percentage of kids who are on the spectrum from their videos of their first birthday by looking at atypical social interactions. But in general, it's rare. Families care, they're loving, they don't know what they're looking for. Not everyone wants to fear all the time, like, oh my God, my baby is not doing all these things. So babies get diagnosed late. The sooner the better. Therefore, 2 is about when people can detect relative to speech and so on. So that's why we wouldn't have, but we did work with, so the babies actually, it's such a great question, I really love it. The babies we worked with were at risk for physical behavior delays. But it turns out there's a combination of that with babies who are on the spectrum. So often babies on the spectrum, autism spectrum, also have motor differences. So a lot of the babies in our study were babies who had older siblings who were on the spectrum, diagnosed. So that's like the whole story, but the diagnosis problem is really hard. It's really hard. Like, there's all this stuff about different doctors will diagnose kids very differently, so it's not a science yet. I hope that helps. And by the way, it doesn't matter where you are, you can still do interesting work. I just want to make that point to young people. Like, don't use any excuses about like, I'm at this university so I don't have this opportunity, or I'm in this job now and I can't do this. Don't do that. Don't do that. You own your life. You own your life.